pi over 180, so that I could just do it this way. Exponent times minus 60 times d times I. And the d does the conversion for me, and I think of it as degrees. And the reason I would do that is because that's essentially what MathCAD does. The little DEG that you see in all the handouts that I give, if I actually asked what DEG was, it would be pi over 180. That's just a number. And so DEG has, it's just a factor. Are we okay on that one? Mm-hmm. Before that, there was a part A and a part B, which asked you to find the phase margin and the gain margin and the delay margin. So how do you do that with this? In order to find the gain margin, which is the first one, how do you do that? Because you almost certainly have a problem similar to this.
From 0
So to find the gain margin, I have to find what first? Yeah, where the phase plot crosses 180. And it turns out to be like about here. And then I look up on the next plot, and I don't have this drawn terribly well. This turned out to be negative 20, about 22 dB. So 0 was right about here. So what is the gain margin? And I want you to draw things on the plots to show me how you got it, okay? Draw some lines and other things so you can show me how you got it. That's your work in this case. So what is the gain margin? 22 dB. A phase margin. What do I look at first? Which plot crosses what?
0.
Where the top plot crosses 0 dB.
Mm-hmm.
So if this is the 0 dB line here, I find this point and then I take it down to here and I figure out how much angle we have between here and here. When I read this, this isn't shown very accurately, but it's about 47 degrees. That means, I'm sorry, it's 47.2 degrees. So if you have a 0.1 or a 0.3, the red ink comes out like blood out of your veins.
Sure.
No, it's difficult to read. And all of these plots are difficult to read. But that's your phase margin. Finally, how do I get a delay margin? Do I have enough information yet to give me a delay margin? I need to know the frequency at which this occurs. Now, my plots are correct. It happened to be where this crossed was, in this case, at about 60 rads per second. So obviously my plots are off, right? I'm sorry about that. So that's the best I could do. So if we got the phase margin equal to 47 degrees at an omega equals 60 rads per second, how do I turn that into a delay margin? What do I need to do?
45.
If you don't know, write it down on your yellow sheet.
Right now.
It's already on there.
It's already on there. Okay, there we go. Look it up on your yellow sheet. I have to turn this into a period. So since period is equal to 1 over f, it is also equal to 2 pi over 60 radians per second. So what is that number if I do that? When I do that, I end up with the period is equal to 0.105 seconds. So 105 milliseconds, let's put it that way. 105 milliseconds when I do this. So it can't be 106, and it can't be 107, and it can't be 103. So how do we change that into a delay margin? This period represents how many degrees? So we're going to look at the fraction of the degrees. So that's fraction of a cycle times the period gives us the time 47 degrees represents. And that turns out to be 14 milliseconds. And that's my delay margin. Now here is where you want to show me in the lines on the graph where you got your numbers and stuff. Because your numbers could easily be different than mine. So make sure you show me where you got them from. Other questions? Yes?
I was hoping you could help me out with problem 4 on 2016.
4 on 2016. Let me find it. Okay. This is right back to early stuff. Signals and pole locations and transforms and that sort of stuff. So what we have here is this. We have like this in the time domain. We have a signal shown that does this. I'm doing my best again, which I know isn't very good, but it's best I can do. Whoops, it's not doing it. Yep, should have projected these.
What is he doing?
Okay. It says, this is the unit step response of a system. Yeah, it's shown. Okay, the unit step response. This is time in seconds this way. This line up here starts at 10. There's a couple of other lines in here. One, here's 0.6, here is 0.3. There's, 0.4. There's a little dotted line across here like this, and one across here like this. Designed to help you figure things out. And it says, find to the Laplace transform of the unit step response, y of s. Should be find the Laplace transform of the unit step response, y of s. So this is a graph of y of t. So you're asked to find y of s. Well, what's step 1 before you find y of s? What do I need to find? Don't I need to find y of t?
Mm-hmm.
Yeah. So what is y of t? What does it look like? First, is it a cosine wave or a sine wave?
Sine.
It's a sine wave. How do you know that?
Starts at 0.
Okay, how am I going to figure out the frequency of that sine wave?
Period.
So if I write this, if I look at that on my graph, I see that it crosses there at 5 seconds. So this is 5 seconds. So how do I translate? Well, over here, we had to translate radians per second into a period. So how do I translate a period into radians per second? F is equal to?
2 pi.
Omega is equal to?
2 pi f.
$1.26. So what do I put in here in the sign? 1.26 t. Good. But it's not just a sign, it's an exponentially decaying sign. How do I figure out what a is? Well, this could also be thought of e to the minus t over tau, right? Now you've done this once or twice before when I've asked you what tau is, and you look at a and you do what to it to find tau? What's the relationship between a and tau?
Oh, it's the rise time?
Yeah, so well that's how we can figure it out. But the relationship between a and tau should be pretty clear from what I've got on the board here.
E is 1 over tau.
Yeah, so can I find tau up there from this? Now the question is, which of those two dotted lines is there to help me find tau? So is it the 0.37 line or the 0.63 line? 0.37. Because remember, it makes it most of the way from the initial value to the final value in 1 tau. That's most of the way, that ain't. So this is most of the way. If it was something that was expanding or something like this, we'd have most of the way like that, right? So what we need here is the second or the bottom line. And when you read that, it turns out that it crosses here right about 4 seconds. So what is tau?
One fourth.
Tau, not a. What is tau?
4.
4, yeah, it's 4 seconds. It's 4 seconds. So that equals tau. So what is a? So this ends up being negative 1/4. Now you can also do t over 4. Of course, negative 4 over t. That's 1 over t over 4. Is that it? Is there any DC component to this? If I had drawn it correctly, you would have seen that it goes to 0. So there's no DC component at all. So do we know what this looks like as y of s? What is our b term? That's our a term, that's our b term. So what goes on the top? Oh, is there one thing that I'm still missing here?
Gain, right?
Yeah, there's one factor still missing here. How big is this whole thing?
10, right?
What number should I put in front here?
10.
Yeah, and the reason is because the amplitude of this waveform started at 10, even though it didn't actually ever reach 10. This is that dotted line there that helps us. So we need a 10, and then what else on top? Because it's b, little b, divided by, we can do this in a couple of different ways. I choose to do it this way. Minus plus a squared plus b squared. There's several different ways I can show this, right? So what is this all about? It's relating what we've been using all of this time in all of these different problems back to the real world. If you haven't figured out by this time, I'm a big believer in the real world. That if you can't relate the stuff we learned in this class to the real world, it is absolutely pointless to have gone through the process of learning it.
Can you explain the numerator one more time?
The 10?
Yeah, no, just the entire numerator.
Okay, if you look at this and you figure out what the Laplace transform of that is, the Laplace transform of this piece is b over s squared minus 2as plus a squared plus b squared. Or two other forms as well, right?
Right. Okay.
But remember this little b up here? For the cosine, there's not a b up there. What is there instead?
Just one.
S minus a.
Yes.
S minus a. But for the cosine wave, it's a b. I do have that right, right?